All right, so I'm going to record my lesson. Today, right, I'm going to resume the electrochemical tutorial. Right, so let's do a recap of what we have done so far, shall we? All right, so let's look at the paragraph over here. Eh, doesn't reflect. How come? Share screen already. Aria is late or absent? Oh, okay, sorry. So let's look at the recap. Okay. Shall we look at this paragraph and try to fill in the blank? So from question 3C, right, you learn something is different from question 5. Right? Then for question 6, you learn something else. Then question 7, you also learn something else. Okay, can you try to look at this paragraph and fill in the blanks? So if you don't know what's going on, maybe you can copy this down so that it reminds you what is the thinking process. All right, so these are your thinking process. Of course, it will only make sense if you practice it regularly. Of course, if you know already, then don't need to copy down. That is if you cannot remember, you need a reminder, then you copy this down. The questions referring to here is your tutorial questions. Okay, so I want you to compare and contrast. What's the difference in context? Okay, if you're not copying down, can you tell each other, your neighbor, what's the answer? Fill in the blanks. More or less fill in the blanks. You are confident of the thinking process? Okay, this one is for electrochemistry. It's different from electrolysis. Electrolysis is another set of thinking process. All right, but it doesn't mean that it's mutually exclusive. The idea is the same. It's just that we need a battery to push a non-spontaneous reaction. Okay, so for question 3C part 1, right? The question right away tell you that you are working with half cells. And I hope you still remember what is the definition of a half cell. Is a reaction mixture containing an element, okay, in two different oxidation number. All right, okay. So when you are working with half cell, two half cells given to you, you have to decide which one is the cathode first. Okay, so what is the thinking process? How do you know which one is the cathode? The one with the more positive. Okay, so I prefer to use the word more positive instead of just greater value or smaller value, because the value comes with positive and negative sign. Okay, it will be clearer if we refer to it as being more positive E0 value. Okay, so remember our standard electrode potential is by default a reduction process. Okay, so the one with a more positive E0 value will naturally be the cathode because it has a higher tendency to undergo reduction. Okay, so what is the significance of this? So why do we choose a more positive E0 to be the cathode? That is to ensure E0 cell, okay, when I combine any two half cell, right, by right, E0 cell will naturally be more than 0. So when I connect two random half cell, okay, it should be able to generate electricity. Okay, as long as that's the potential difference. Yeah, okay, all right. So for question 5, the species that we are looking at, okay, so remember for question 5 and question 6 onwards, we are no longer working with half cell. Okay, we are only looking at a particular reactant. Okay, there's only one reactant. It's no longer having elements in two different oxidation number. Okay, so that particular element can only undergo oxidation or reduction. Okay, so for example, if I'm having a metal as one of my reactant, then you have to recognize that metal cannot become M minus. It can only become M plus. So metal can only undergo oxidation. All right, so there's no way you can have M minus, right? This is impossible. It can only be oxidized to become M plus. Okay, so metal can only undergo oxidation. So this means that by default, the other reactant must undergo reduction. Okay, so if the other reactant must undergo reduction, it must be on the left side of your half equation. Logic? Okay, so when you're working with question 5 without the half cell, then you have to look at what is given to you. Okay, and you need to recognize which reactant can only go one way. All right, so if the other reactant happens to be a non-metal, then you need to recognize that it can only undergo reduction because non-metal tends to form an ion. So therefore undergo reduction. Okay, so this means that the other reactant must undergo oxidation. So if the other reactant is to undergo oxidation, then it must be on the which side? Yeah, the right side. Okay, so these are your thinking process. All right, so after verifying that the given reactants appear on the opposite side, okay, so it's not always two reactants, they will always automatically appear on the opposite side. Sometimes they appear on the same side. So if they appear on the same left side or appear on the same right side, then there will be no reaction. You don't even need to calculate E0 cell. You should know that a redox couple is not formed, therefore no reaction at all. Okay, so after verifying that they are on the opposite side, that is still not a sure can react, cannot guarantee a reaction. You must still calculate the E0 cell. Okay, and the E0 cell has to be more than 0 in order for this redox reaction to be spontaneous. Okay, so this is what you have learned so far. All right, then for question 6, very important, we recognize that the vanadium +5 to +2 undergo a progressive reduction, step-by-step reduction. It doesn't reduce from +5 straight away to +2, one shot, okay? And why so? Why is it so? It's because you notice that from +5 to +4 is a +1. From +3 to +4 to +3, +0.34. And the last one, +3 to +2, is a -0.26. So you can see from this trend that it is decreasingly positive. Okay, the E0 value is decreasingly positive. So it gets more and more difficult to reduce it. Okay, that's why it's a stepwise reduction. It doesn't get more easy. It gets more difficult. That's why it's a stepwise reduction. Okay. So if it gets more easy, then it's another story, right? So therefore, for this question, right, you see a progressive change in color, right? Because each vanadium at different oxidation number has their own unique color. Okay, so you see a gradual change in color. Then for question 7a, what is the learning point? Question 7a, the learning point is your manganate is in highly acidified medium. So being in highly acidified medium, we will only consider reduction to Mn2+. Despite Mn2+, E0 value is less positive than manganese dioxide. Okay, so this is the one that you choose in acidified medium. You don't even consider this. Even though what we have been doing so far is we always choose the more positive one, but it doesn't work for manganese. Okay, right? Okay, so this is what we have learned so far from the tutorials that we have done. Any question? Yeah, manganese is the most often used oxidizing agent. So if you use other oxidizing agents such as dichromate, there's only one possibility. Dichromate to chromium 3+. There's no argument. But for manganese, is the one that it can be +6, +4, and +2. Yeah. So once you know that it's acidified, it's all the way to +2. Don't even need to consider the rest. All right. So manganese is the so-called special one. Okay. So just remember this. Okay. All right. Any other question? Yep. Okay, so this is where we stopped, right? Last time. Yeah, so this is where we learned that with acidified medium, I know that Mn2+ is formed. Okay, then for the next part, how do you get the answer? How do you discuss that? Why is it that manganate with acidification, it must be sulfuric acid, not hydrochloric acid? Why? How do you put that? What will you do? So the only difference between these two acids, of course, is the sulfate ion itself, as well as the chloride ion, right? So that is the essential difference between these two acids. Okay, so how do I justify using the calculation of E0 cell to explain that HCl cannot work, but H2SO4 can work? Okay, so I need to consider reduction potential or oxidation potential. Oh, okay, reduction potential by default. Okay, so in this case, we know that manganate must undergo reduction. So this is my cathode. Okay, so this means that my sulfate and my chloride must be the one undergoing oxidation. So this means that I must actively look out for these ions on the right side of the half equation. So do you manage to find sulfate and chloride on the right side of the half equation? Yeah. Okay, so if you manage to find that, right, then your E0 cell will simply be equals to E0 of your manganate 7 to manganese 2+, which is a positive 1.52, right? According to what I remember just now. Yep, positive 1.52. Then minus away the anode E0. All right, so what is the anode E0? What is the E0 value? So consider oxidation of sulfate. So it's a S2082 minus reduced to sulfate, right? Yeah, do you manage to find this? So minus away this value. So what is this value? Okay, so when you do this tutorial, you have to keep on practicing how to select the half equation for your data booklet. Okay, don't wait for my answer. Don't refer to the notes. Because in examination, Mrs. Kong is not there to give you answer. Notes is not there to help you answer either. So only data booklet is given. So you must know your data booklet well. And that's why I keep reiterating the thinking process. All right. So you must know how to look for it. So do you know how to look for this? Yeah. So this one is a positive 2.01, right? Yeah. So when you subtract, you end up with a less than 0. So with this, you prove that sulfuric acid doesn't undergo redox reaction. It will just be there to provide the H+, which is required for your manganate 7 to become Mn2+. Okay, so with this, we prove that there's no redox reaction. Acid is just there to provide H+. Okay, but in contrast, right, if you replace the whole anode, okay, the oxidation process by minus E0 chlorine to chloride, what do you have? Is a 1.26, 1.36. 1.23 is the H+, water, okay. Yeah, so in this case, right, you minus away 1.36, which is giving you an E0 cell more than 0. So with this, you prove that your manganate is strong enough to oxidize chloride. So if you use hydrochloric acid instead, you're not just providing the H+, you're also providing a reducing agent. All right, and this is not what we want because it's a side reaction. Okay. Can so far so good. This topic should be not so confusing, okay, quite straightforward. Okay, I move on. Okay, so let's look at the next part. Right, predict what you expect to observe when acidified chlorate 5 is added separately to each of the reagent. Okay, so same thing, you are not working with half cell. You are only working with one of the reactant, which is your chlorate 5. So chlorate 5 can only undergo reduction. Right? You're not given a half cell. So as what is suggested here, chlorate 5 can only undergo reduction. So this means that I must consider oxidation of my iron 2 sulfate. Okay, so straight away we recognize that iron 2 is the one that will react, because previously if you try to oxidize sulfate, it's a very negative value. Yeah, okay, so I hope you can recognize that sulfate is not going to be affected because it's difficult to oxidize it. Okay, so iron 2. So where should your iron 2 be from the half equation? If it were to undergo oxidation, where should your iron 2 be? Right hand side. Okay, so you should be looking at iron 2 over here, then coming from iron 3 plus, right? Okay, it's a positive 0.77 volt if I'm not wrong. So when you combine the E0 cell, when you calculate the E0 cell, are you able to prove that it's more than 0? Are you able to prove that it's more than 0? Have you done your work? Minus 0.77, right? So it's more than 0. Yeah, so therefore it can work. So what will be the color change? What will be the color change? Turn green. Why turn green? Your iron 2 is a pale green color. Then when it's oxidized to iron 3, what does it become? Yellow, not reddish brown. I already told you last Friday. Reddish brown is for rust. Rust is iron oxide, iron 3 hydroxide. Okay? Iron 3 solution, yellow. Yellow, not reddish brown. Okay, so remember that. So are you able to write the balance equation? Do I need to show you? All right, okay, so this balance equation, remember last lesson you asked me whether state symbols are required. Well, it seems like the team feels that state symbols are not required. Okay, so when you write the overall equation, right, you can do without the state symbol unless the question asks for it. Okay, but remember, in energetics, state symbol is a must. Okay, so state symbol in energetics, they don't need to ask for it. You must know state symbol is a must for energetics. Do you still remember what is energetics? Enthalpy change? Hess's law. Okay, ring a bell, right? Or sounds familiar. Okay, all right, can I move on? Can balance yourself, Okay, so let's look at this acidified KMnO4. All right, so chlorate 5 only undergo reduction. Then how about potassium manganate here? Potassium manganate also undergo reduction. Yeah, so if both reactants are on the same side of the half equation, can anything happen? Yeah, no reaction at all. So you just need to highlight that both are oxidizing agent or both can only undergo reduction. So therefore, no reaction. So your observation is purple color remains. No reaction, no change, so purple color remains. Okay, so it's either you say both are oxidizing agent or both only undergo reduction, also can. Right? Just tell me that they are taking part in the same rule. So therefore cannot react. Yep. You have to explain now. Yeah, because they ask you predict what you will expect. Yeah, predict means comes with explanation. Unless the question says state. Then don't need to give reason. Yeah, predict. Okay, the terms predict, suggest, or requires explanation. Predict, suggest. Yeah. Reduction. Potassium, okay, among the two manganate and potassium, right, both undergoes reduction. But then K plus reduction process is very negative. Yeah, so between the two, right, I will say that manganate is the one that is more likely to undergo reduction. But then your chlorate 5 also undergo reduction. Yeah. Sulfate cannot pick SO4 2 minus, meaning? Sulfate must be on the right side. SO2 gas. But sulfate is plus 6. SO2 here. SO2 is different from sulfate. This is a plus 6, while this is a plus 4. So when I say iron 2 sulfate, right, it can only be this. Cannot be SO2. They are different. Yeah. Can? All right, so I move on. So let's look at the next part. With a few drops of acidified hydrogen peroxide. Okay, so again, you are not working with half cell. You are just working with one reactant. So hydrogen peroxide. So hydrogen peroxide, if you refer to your data booklet, do you notice that hydrogen peroxide can appear on both sides of the half equation? Yeah. So this means that you have to counter check the other reactant. So the other reactant, you focus on the I minus. Okay, potassium plus, usually we ignore. If it's a main group metal cation in our as a reactant, right, we will ignore it because it's very difficult to reduce it. Yeah, main group metal cation in the solution is very difficult for it to undergo redox. Yeah, so we'll just ignore it. So we consider iodide. Okay, and the iodide, okay, upon addition of iodide, the solution actually turns brown. So you need to ask yourself, what is this brown coloration here? Cannot be due to your hydrogen peroxide. It can only be due to your halogen. Okay, so this means that your iodide is oxidized to iodine. Yeah, iodide is oxidized to iodine. So if iodide is oxidized, then your hydrogen peroxide must undergo reduction, right? Agree? Yeah. So if hydrogen peroxide is to undergo reduction, then your hydrogen peroxide must appear left side, right side? Left side. Okay, so you should be looking for hydrogen peroxide on the left side. And that will correspond to a positive 0.68 volt. Am I right? I'm not asking you to memorize. I just happen to remember. This morning I was just looking at it. Oh, 1.77. Okay, so the other one is a 0.16. Yeah, okay. Yeah, all right. So in this case, right? All right, so your hydrogen peroxide undergoing reduction is an E naught value of positive 1.77 volt. Okay, then what is this value? What is the E naught of this? Iodine to iodide. So you have the E naught reduction of hydrogen peroxide reduced to water lah. So minus away the anode, which is the E naught reduction of iodine to iodide. Okay, so this is a positive 1.77 volt. Then this one is a minus of 0.54. Yeah. Okay, so you end up with a more than zero value. So remember, after you calculate your E naught cell, you have to compare with the value 0. Okay, so it's more than 0, that means it's a spontaneous reaction. Okay, so from here, right, you should expect that because hydrogen peroxide is undergoing reduction, so therefore there's no effervescence. Okay, so you also need to account for this. Why is there no effervescence? That is because hydrogen peroxide is all undergoing reduction, not oxidation. Okay, if hydrogen peroxide undergoes oxidation, that is your O2, but that is not observed. Can? Okay, so I hope you know what does the effervescence refer to. In physics, right, do you learn Faraday's constant? Oh, yes, right. So do you learn how to calculate? I mean, what's the calculation involved when you use Faraday constant? So do you also work with electrolysis also? Huh? What circuit? What is that? You work with circuit. Huh? You don't use it a lot. Okay, can. Huh? I2, yeah. Yeah. So I2 here is the brown solution. Okay, yeah, I know that iodine is not really soluble in water. So the brown solution is actually something else. So you just know that iodine is, some of it can dissolve in the aqueous medium to give you the brown solution. But if there's more iodine, right, it will exist as a black PPT, dark color PPT. Yeah. So the brown solution, right, the solution turns brown refers to the iodine that is dissolved in it. So the thinking process here is you must recognize that the coloration is due to your halogen, not due to hydrogen peroxide. Yeah. Okay, Ken? Right, any other question? Tomorrow is your HBL. You're supposed to complete the rest of the tutorial. Some of you, yeah. So if you really struggle with it, then you must clarify. Yeah, don't just keep quiet. Okay, I move on. All right, so if you look at A, question 8A, E naught values from data booklet. Use E naught values from data booklet to show that the reaction between the two is unlikely to occur. All right, so if you look at copper 2 sulfate, okay, like I say, right, sulfate is unlikely to take part in the redox. Okay, it's very difficult. All right, so if you look, sulfate reduction to SO2, sulfate reduction to SO2 is a very small positive value, right? Yeah, it's a very small positive value. I mean, even if you want to consider, it's fine lah. Okay. 0.17, 0.17 volt. So it's even smaller than but it's comparable to copper 2 to copper 1. Yeah. Yongwei, do you know why you don't choose the SO2 one? because you must recognize that you are considering sulfate on the right side. Yeah, SO2 is also on the right side, but SO2 is not the reactant here. Yeah, okay, you must know which side to refer to first. Okay, so sulfate can also be considered, but it will not be the one taking part. Okay, so you need to see that potassium can be ignored because it's a main group metal cation. So you are considering iodide. So iodide, according to your data booklet, is only found on the right side. Okay, which means that it can only undergo oxidation. Okay, so if iodide can only undergo oxidation, then your copper 2 must be undergoing reduction. That's why your copper 2 must be on the right side. Okay, so when your copper 2 is on the right side, between these two, you will choose this because it's more positive. More positive, right, has a higher tendency to take place. So we will ignore this. And if you are also considering sulfate, which can also undergo reduction, but it's a positive 0.17. So less positive than your copper 2 to become copper 0. So we will also ignore this. Can? We consider water. Water is a negative, but reduction of water is negative, right? It's not positive. Yeah. Oxidation of water, also negative. Huh? Negative 1.23. Yeah. Yeah, also negative. So water, right? You only consider participation of water when you consider electrolysis. Yeah. If not, right, all your aqueous reaction in the lab, water starts to come in. All your aqueous solution, water is there, right? Then water is a side reaction. Then how? What are you going to do? And water reacts with your body system. That's very dangerous, right? If you drink water and water creates a lot of side reactions in your body. Cannot, right? Yeah, think about it. All right, so water is only considered if it's electrolysis, not for electrochemical cell. Can? Most often, most often. But if you are working with a reactive metal, then water can react with it. Reactive metal. The metal very reactive, right? The E-ox is very, very positive. Yeah. The metal can undergo oxidation, then your water can be reduced. Yeah. Do you see that reaction before? Reactive, like sodium metal or potassium. Then you put it in water, then there's a lot of, it's explosive. That is because it's it's a very positive E cell. Okay, so this one, please take note, this is not considered because there's no ammonia provided in the system. All right, so this only becomes relevant if there's ammonia provided. All right, so you must choose carefully. So not any random copper 2 will apply. All right, of course, if you compare the E0 values, this one is negative, so it will be out of picture. But that's not the only reason. It's also because ammonia is not there. All right, so do recognize that. So with this, right, you are able to calculate the E0 cell, and it's proven to be less than 0. So thermodynamically is not feasible. Okay, or not spontaneous. So we use the term not spontaneous, okay, to represent thermodynamically not feasible. Can? All right, so this is what is happening. So let's look at 8B. With dilute copper 2 sulfate added, blah, blah, blah. So do you still remember how to calculate the empirical formula? Yeah, okay, so with the calculation, you should be able to tell that this is a copper 1 iodide. Do you manage to get this? This is the green PPT, all right, so okay, so just now in part A, we just proven that the reaction between copper 2 and iodide doesn't take place. But then this reaction is involving the same reactants. There is a product form. So that is the apparent contradiction. Yeah, so this is what we are talking about. Why is there a contradiction here? Because in part A, we have predicted that using E0 cell cannot take place. Yet, in lab, when you add them together, there is a PPT form. There is a reaction. So why? Why so? What do you think? Okay, Now, if you try to calculate the E0 cell again, so please take note. The reaction is forming a copper plus. It's not a copper zero. So if you choose the relevant half equation from here, copper 2 to become copper is a positive 0.15, while the iodide to iodine is a positive 0.54. So if you calculate the E0 cell again, based on what is the product form, okay, it will be a positive 0.15 minus a positive 0.54. And obviously, it's less than 0. Yeah. Okay. Even more negative. But why is it taking place? Who can tell me? It's even more negative than part A, right? Yeah. So why is it taking place when it's more negative? Do you know why I consider this? Because the copper 1 iodide is +1. Okay. So we are using this half equation instead to calculate. Yeah. So why? Who can answer? Instead of me giving you the answer, now it's your turn to tell me. Yeah. Wow. What's the answer? Remember, this E0 cell is based on what? What is the significance of this pi symbol or chi symbol or whatever symbol? Standard condition. Standard condition means what? Your ions must be 1 mole per dm cube by default. Any dissolved species in the aqueous medium must be 1 mole per dm cube. Okay, then? Okay, now my question is, how do you know that the concentration becomes different? How do you know that? How are you so sure that the concentration is different? It's not 1 mole per dm cube. How do you know that? You are right. Okay, the moment we use E0 cell, because of the phi symbol, we are assuming that this reaction is taking place under standard condition. And standard condition means what? Temperature 298 Kelvin. All the dissolved ions or species in water must be 1 mole per dm cube. Now back to the question. How do you know that this reaction doesn't involve ions 1 mole per dm cube? How do you know that? CUI is what? CUI is formed. So the formation of CUI, how does that help me explain that it is no longer under standard condition? How? CUI, okay, so what's wrong with CUI? Can form CUI or what's wrong? Because it's solid state. So what's the significance of CUI being formed in solid state? Yeah, so if you look at this half equation, we are assuming that copper 2 is 1 mole per dm cube. Copper 1 is also 1 mole per dm cube. But just now I highlighted that the copper 1, which is formed as a product, is not a copper 1 aqueous, but it's a copper 1 iodide PPT. So this means that during the reaction, your copper 1 concentration can never hit 1 mole per dm cube. It's always very, very low. So when the concentration of copper plus is always kept very low, what is the effect on the E0 value? What is the effect on the E value? What is the effect? Yeah, it will become more positive. It will favor the reduction process. Yeah, because the product now cannot hit the 1 mole per dm cube. It's always kept very low. Yeah. Okay, so this is what is happening over here. Right, so the apparent contradiction is, you know that we predict to be less than 0. So unlikely to react, but yet there is a reaction. Okay, so we need to highlight that copper 1 solid PPT is being formed. Okay, not this. Right, so this means that your copper 1, right, is never at or can never hit 1 mole per dm cube. It's also constantly kept very low in concentration due to precipitation of copper 1 iodide. No. Iodide is oxidized. The reaction is between copper 2 and iodide. So the iodide is in excess. This is present in excess. So once the copper 1 is formed, it will combine with the I minus to form a PPT. Yeah. Is the last sentence relevant? Meaning? Oh, no, because there's a minus sign in front. I just want to cross that away. Yeah, because sometimes, right, don't know why there's a minus sign in front, or is it just a bullet? Yeah, I don't want you to mistake it to be a minus sign. Yeah, so I cross it away. No longer E naught, because it's the deviation from standard condition. So we put it as E value.
It must become 0.5. It must be more than or equal to 0.5.
Yeah. Yes. More positive. We just say, no need. Oh, yeah. Understand. Yeah. Understand. So the reference here should be more positive than 0.54. Is this what you're trying to say? Yeah. Okay. Yeah. So Iman is right. So I should say that it has become more positive than 0.54 because if according to the equation, you subtract this away, so in order for this to become more than 0, it must at least become more positive than 0.54. Yeah. Iman is right. Can? Yeah. Sounds reasonable, logical. Hmm? Yeah.
Because when you add two solutions together, it's still less than
But if it's less than 1 mole per dm cube, then it will not favor the reduction process. Then it will contradict even more. Yeah. It doesn't explain the phenomenon. Yeah. So what you need to focus on is to explain the phenomenon. Yeah. Okay, so can I move on? Is this the last part already? All right, if you're interested in the equation, right, this is what the equation will look like. Yeah. So this is a few years back, right, quite a popular A-level redox titration in paper 4, practical assessment. Okay, so when they started the new syllabus practical assessment, in the second year, they asked students to carry this out, a redox titration involving copper 2 and iodide. So during the titration, right, everything becomes very dirty because iodine is brown and there's white PPT swimming around in your solution. Yeah, so everything is very dirty. So yeah, so we did you do it last year? I can't remember. Yeah, of course you did hydration, but then I don't know whether you did this hydration. Yeah. Okay, yeah. So this one, you will see this again when you start your transition metal. Yeah, you still have transition metal. All right. So if there's no further question, I hope that tomorrow you go and practice your thinking process again using 9 to 12. And question 12 requires graph plotting. So you need to use a graph paper. And I hope you still remember how to do graphs for reaction kinetics. Okay, graphs. Oh, during the June holidays, do you want me to put up consultation slots for you all to come for consultation? It can be online or face-to-face, up to you. But I prefer online, then I can stay at home. Yeah, I don't want to come to school also. You don't want to come to school, I don't want to come to school. I don't want to come to school every day. Yes, what is it? Can? All right, so I put a consultation slot. Sebastian. Okay, so let's look at the electrolysis. Come. Let's look at the new topic. Yeah. Okay, so electrolysis should be more straightforward, I think. Yeah. Okay, so these are the learning objectives. Then let's look at the setup. So electrochemical cell, as suggested, is a spontaneous reaction. So you just connect any random half equation, electricity should be able to flow. So that is electrochemistry. Okay, but for electrolysis, right, we don't work with half cells anymore. What we are trying to do is we are trying to use electrical energy or a battery to push a non-spontaneous reaction to occur. Yeah, okay, so that is the essential difference. All right, okay, so do you still remember why is anode negative polarity while cathode is positive polarity for electrochemical cell? Do you still remember? Sebastian, remember, I know. The rest, eh? Okay, can you tell your neighbor? Okay, if your neighbor is not present, then yeah. Can you tell your neighbor, revise a little bit? In electrochemical cell, what makes anode negative, cathode positive? Okay, so for physics, you only look at the external part of the battery. For chemistry, you look at the internal part of the battery. All right, so this is what the internal look like. Okay, so the salt bridge is there. Okay, so in this case, right, can I request? Okay, so what I've done here in this diagram is I cut and paste the electrochemical cell. Then I remove the voltmeter. Then I put the electrolytic cell in place of the voltmeter. Can see that? So voltmeter is gone. All right, now it's replaced by the electrolytic cell. So in this electrolytic cell, the electrode, so let's focus on this electrode. This electrode, which is connected to your anode. All right, remember, voltmeter will receive electron from an anode, right? Okay, so likewise, this electrode will also receive electron from an anode. So as it receives electron from an anode, it will undergo reduction. Okay, the electron is from the electrochemical cell. Okay, so as it receives electron, it will undergo reduction. So therefore, it will be the cathode. And in this case, because it's connected to the anode, it will assume a negative polarity. Yeah. So you notice that, right? For electrolytic cell, where you have cathode, the polarity is opposite to what you have for electrochemical cell. Make sense? It's opposite, because in electrochemical cell, cathode is the one with positive polarity. But now with electrolysis, it's receiving electron from the anode, right? Hence, undergoes reduction. Now is the cathode. Cathode connected to the negative anode of the electrochemical cell, right? Can? Right? So if you look at the other electrode here, this electrode is connected to your cathode of your electrochemical cell. So it will follow the polarity, positive. Okay? So here, right, it will lose electron to your cathode of your electrochemical cell. So losing electron means that it will undergo oxidation. So oxidation means it becomes the anode. Right? Okay, so remember, anode and cathode is always defined by the process. And anode is oxidation, red cap reduction is the cathode. Yeah, can? Make sense? All right, okay. All right, so can you amend this polarity of the electrode in electrolytic cell? Always follow the polarity of your battery. Okay, to make it clearer. Can you amend that? And ox with cat. Okay, so just remember polarities are reversed. So if you don't quite understand what I said just now, it's okay. You just remember it's opposite. Okay, move on. Let's look at this. Page 3. This setup is quite easy, right? Okay, so please take note. Electrolyte is present in the electrolytic cell to maintain flow of electrons, or rather to close the circuit. Okay, so this is what is already discussed. Okay, the table is for you to see a contrast, so you can digest on your own, right? So I just want to highlight the third point. What is an electrolyte? So electrolyte is a mass in electrolytic cell. So electrolyte is defined as mobile ions, which can help us conduct electricity. All right. So this mobility can come in two forms. Number one, in molten state at the melting point. All right. So when it melts, ions can become mobile, therefore can conduct electricity. All right. Another physical state will be aqueous state. In aqueous state, if it's soluble, it can also dissociate in aqueous state to form ions. Therefore, become mobile and conduct electricity. All right, so there are two forms. So page 4, very straightforward. You are working with molten salt, and there's only one salt. So very easy. Cathode, there's only one cation to consider, lead 2+. Anode, there's only one bromide ion to consider to be oxidized. JAE student, you have learned this also, right? Okay, so this one I can speed past. Very happy. Woo! So let's look at page 5. So now we are looking at page 5. No longer in molten state, but there is aqueous medium. So this is when we need to consider the participation of water as well. Okay, so please take note, water usually not for electrochemistry, but for electrolysis most often. Okay, and you can be looking at a mixture of salt as well. Okay, so this means that the concept of selective discharge becomes important. Okay, so we have to choose an ion or species to be discharged at the respective electrode. And what are the considerations? All right, the consideration that we need to talk about to go through is what is the relative E0 values. Okay, that's number 1. Number 2, concentration, because concentration of the ions can affect the POE. When the POE is affected, it can affect your E0 values. So therefore, it can also affect how you select the ions or species undergoing discharge. Okay, then the third one is your electrode. Whether this electrode is an inert electrode or a reactive electrode. Okay, inert electrode are most often your platinum or your carbon, most often. Carbon sometimes can also react, depending on what is the product. Okay, so reactive electrode are those that other metals are. Okay, so these are the 3 factors. So for this, we'll just focus on this first. Okay, so what is happening is at the cathode, we are considering reduction process. Then among the species, right, we'll choose the more positive E0 to undergo reduction because it has the highest tendency. Okay, highest tendency. Then for oxidation, right, then of course we are looking at the reverse process. Then the more negative it is or the less positive it is will be the one chosen to undergo oxidation. Okay, all right. So blah, blah, blah. So can you use this term instead? Can you help me change? It's not about how fast, it's about tendency. So use the term preferentially reduced. Okay. All right, blah, 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 blah. Yo. Okay, so in this case, right? So look example number 2 on page 6. Right, so when you have an aqueous solution containing a mixture of salts, so these are the species that you need to consider, right? Copper 2, silver plus, nitrate, and water. Okay, so when we are considering cathode, which undergoes reduction, then we must actively look for this species on the which side of the half equation? Left side, left side of the half equation. So these are the species on the left side. And which one is the most positive? Silver. So silver being the most positive will be the one that is preferentially discharged. So similarly, if you are talking about anode, then the species must be on the right side of your half equation. So if you try to look for the nitrate, right? Don't put out your hand and say, teacher, I cannot find nitrate on the right side. Okay, please recognize that nitrate here is already at +5 oxidation number, which is the maximum. Okay, so there's no way nitrate can appear on the right side because nitrate cannot be further oxidized. Okay, so once you see nitrate, you don't even need to consider oxidation. Impossible. Okay, so even though it's an anion, it doesn't mean that it can get oxidized because it's limited by the maximum oxidation number. Okay, so not all non-spontaneous reaction can be driven by battery. All right, okay, can. Right, so there's only one choice, which is water, and it will be oxidized to oxygen gas. Okay, blah, blah, blah. The rest you can read on your own. All right, so part B, right, I want to highlight, part B. Only consider participation of H plus or OH minus if you are using acidified medium or alkaline medium, respectively. Okay, so if just aqueous, no H plus, no OH minus. Okay, so only consider H plus when the question says there's acid. Only consider OH minus when the question says there's sodium hydroxide used or there's an alkaline medium. Can? Right, so if it's just aqueous, no H plus. If it's just aqueous, right? I mean, okay, JAE, when you talk about electrolysis of water, do you talk about consider H plus and OH minus? Is this what you taught? I mean, last time. Has it changed? So when you consider electrolysis of water, that's it sure you don't learn the H plus and OH minus anymore. Oh, okay, then good. All right, so please remember this is not applicable. This is not applicable. Okay, if it's just aqueous medium. Can? All right, this is the only thing that I want to highlight to you. Then the rest you can read on your own. I think it's very straightforward. Right? Straightforward, right? Okay, very boring. Okay, so let's move on. Okay, let's look at checkpoint 1. Okay, now is for you to work harder. Checkpoint 1. Because the concentration is much less than 1 mole per dm cube, 10 minus 7. Yeah, so that will not be the inert value. Yeah, so we should consider water. Yeah, not H plus and OH minus, unless we put acid or alkaline. Okay, so can you work on checkpoint 1 now, page 7? Actually, Lashana, when I stand here, do I block you? I block you most of the time, is it? Sometimes, oh, okay. So if I block you, you tell me, okay? I mean, I'm just very used to standing there. Hmm?
So for example, this sulfate, right?
Yep.
We cannot use this one. Cannot use this equation.
No. Sulfate, right? If you are considering reduction of sulfate at the cathode, yeah, can consider.
Then why just now you use this one? S2O.
Oh, that's because I'm considering oxidation of sulfate.
Then
Which
this
question? Which question? You tell me which question first.
just now the tutorial.
Yeah. Then I'll tell you one. No, the question paper.
This one.
No, because we know that chlorate must undergo reduction. So this must be oxidation. So my species undergoing oxidation can only appear on the right side. So my sulfate must be on the right side. This is what I'm talking about. Because we already know that this can only undergo reduction. Then the other reactant must undergo oxidation. So your sulfate must be on the right side. The sulfate here is on the wrong side. So cannot consider. This is what I meant. Yeah. It's not a half cell. If it's a half cell, then you can consider. Yeah. Because half cell means that both are present. So you can either go this way or that way, depending on what's the other half cell. So that's why I started off the lesson with the contrast between the difference between half cell and not half cell.
Sodium cannot be used, right? Because it's a main.
Yeah, main group metal cation difficult to undergo electrolysis. I mean, you can still list down, but you end up with the same conclusion. Yeah.
Reduction not considered.
H2O.
Like for this equation, why is this not considered?
This is not H2O.
As in,
But this is not present. Yeah, because H2O is just H2O. Yeah, so I don't consider the presence of other species unless it's mentioned by the question. Yeah.
Where's the battery?
Oh, where's the battery?
Why got no battery?
Oh, it's here. Then there's a wire here. Then positive electrode. It's just that it's not shown.
So the electrolyte is like
Yeah, the electrolyte is your, this one. Mobile ions, aqueous ions.
This is more positive than this reaction. Why is this the oxidation of water?
But there's no water here, it's hydrogen peroxide. Huh?
Like
Oxidation.
of water.
Then it becomes negative because you are trying to reverse the process.
Yeah.
Then the reverse process, you should choose a less positive one or more negative one. Because it's reverse.
How is hydrogen produced? Because this one is if the water was reduced,
Yeah.
but then like, I got that something was reduced.
Cannot be.
But it's like more positive than this.
Water here, negative.
And something is 0.17. So shouldn't it be SO2 that's produced instead of H2?
Yeah. Cannot be. No, we never consider sulfate. Careful. Yeah, you're right. It's more positive. Oh, wait. Sulfate here. Sulfate need H plus. Okay. Okay, right. So let's look at the answer, please. All right. So the species present according to your sodium sulfate aqueous, right? There are your sodium plus. Okay, so let's identify the species present. So there is a sodium plus sulfate and your water, right? So at the cathode, you should recognize that it can only undergo reduction. So this means that I should actively look for species on the left side. Okay, so we should look for water, sulfates, and sodium plus on the left side. Okay, but notice that I only choose these two, ignoring sulfates. Do you know why? You can't reduce sulfate. You can. There is a reduction potential for sulfate here. In fact, it's about 0.172, according to your data booklet. Yeah, there's no acid. So this half equation can only occur when there is an acid provided. So the question never highlight is an acidified medium. So therefore, this cannot occur without the presence of the acid. Okay, this is not present. So this half equation is not applicable. You must recognize that. Okay, so it looks like it's the most positive, but because something is lacking. Okay, remember, if your half equation has H plus, and if it's not present, then that will not occur. Remember that. So likewise, manganate to Mn2 plus, no H plus, right? Then that reduction process will not occur. Okay, so certain reduction process can only occur with the help of H plus. Can? All right. So between these two, this one is the more positive one. Now, can see that this one is more positive, right? So therefore, this will be the preferred reaction taking place at the cathode. Okay, so at the anode, this is where oxidation takes place. So for oxidation, what can you consider? For oxidation, what can you consider? Yeah, the sulfate oxidation as well as your water. Okay, so don't remember, always remember water in aqueous medium. So between these two, the one that is less negative, the one that is more less positive, more negative will be the one undergoing oxidation. Can? All right, so between these two, obviously is oxidation of water. Can? Okay. Any question? Yeah. Okay, so let's move to part B. Explain why the volume gas are in the ratio of 2:1. So 2 of what to 1 of what? Huh? What's the ratio? So I hope you recognize that with every reaction, if you look at the number of electrons transferred, if you try to balance the half equation, this one will be multiplied by 2. So for every 4 electrons transferred across the anode to cathode, right, then you will see the hydrogen gas producing 2 mole, while the oxygen is producing 1 mole. Yeah, with the same number of electrons. Okay, so for the same number of electrons transferred, this will be the mole ratio of hydrogen and oxygen gas evolved. So that's why is 2:1 ratio. Okay, quite straightforward, right? Then still explain the color of the limits. So what's the color? At the negative electrode, what color do you expect? Blue. Why blue? Yeah, OH minus is produced. So water is reduced to OH minus. So therefore it makes the solution around there alkaline. Therefore litmus will turn blue. So on the other hand, for your anode, right, H plus are produced. Okay, so this means that the litmus will turn red as a result. Right? So when you combine the 2 half equation, right? So what happens when you combine the 2 half equation? You will see water decompose to form hydrogen and oxygen. When you combine the reduction half and the oxidation half, you will see water decompose to form the elements, hydrogen and oxygen. Okay, so very quickly, right, let's look at page 8. Right, so what we have done in checkpoint number 1 is we are just considering the species that's present, then choose the species that can undergo discharge based on their E0 values. All right, so now next, for this part, we are going to look at the effect of concentration. Okay, so sometimes concentration can override the E0 values if the difference between the competing E0 values is small. Okay, small. All right. And most often the example that we are looking at is with respect to sodium chloride, brine. Okay, so this is what is stipulated in the syllabus. So you must recognize that when I choose brine instead of dilute sodium chloride solution, then I should recognize that chloride will be the one that is preferentially discharged. Okay, instead of water. Yeah. Yeah, so for your syllabus, small is for chloride to chlorine is a negative 1.3 something, 36. Whereas for water, right, is a negative 1.23. Yeah, so small enough means like, I cannot tell you whether it's small enough or not. Yeah, I mean, what is required in the syllabus is you must recognize that if it's sodium chloride versus brine, then it's small enough to change. Yeah, if there is a bigger difference, then it must be implied by the question. Yeah, so you have to read the question carefully, whether it implies that there is an override. Yeah. Actually, you are the one who supplies the battery one. So if you use a larger voltage battery, anything can go up, isn't it? Logically. Okay, anyways. All right. Let's not go into that. Okay. So points to ponder. Are the products at the cathode expected? So if you consider dilute sodium chloride solution and you compare the E0 values, sodium plus and water, between that, obviously water is the one that is preferentially reduced because of the more positive E0 value. So that is expected. Okay, so if you look at part B, are the products at the anode what you expect? Same thing, you consider oxidation. So you see oxidation of water versus oxidation of chloride on the right side. Okay, then you see that, oh, E0 value of water is actually less negative. Yeah, more negative. Less positive. So therefore, the reverse way is preferred. Yeah, can? Yeah. So as long as you are not confused. I'm confused is okay because I'm not the one taking exam. You cannot be confused, huh? All right. So please take note, please don't use the term yeah, in your notes, I think they just use this, right? Can you change that? Say less positive. Okay, so it's less positive than chlorine to chloride. Therefore, it will be the one that is preferentially oxidized. Can? So what happens when you use a concentrated sodium chloride? So if you look at the table, right, if you replace the dilute sodium chloride solution with brine, okay, so learn this word, brine. Brine means that it's highly concentrated sodium chloride solution. So you notice that even though the reaction at the cathode stays the same, but the product formed at the anode becomes different now. Okay, so this is the so-called unexpected. Okay, so why is there a change? Yeah, so why is there a swap in the oxidized product? So that is because of the concentration factor. Okay, so with high concentration of sodium chloride, you get your E value becoming even less positive, or the reverse direction will be preferred, right? More preferred. So that's why if it becomes less positive than your E naught value of water, then it will be the one that is preferentially oxidized. Okay, so that's why chlorine is produced instead of oxygen gas. Can? So that is playing with the concentration factor. Okay, so as long as it's sodium chloride versus brine, you should know this is the expected observation. Okay, as stipulated by your syllabus. Blah, blah, blah. Okay, so what is the difference in the electrolyte? What will happen to the ions in the solution? So if you look at dilute sodium chloride, it's basically just decomposition of water. So the H plus and OH minus stays the same. Okay, it will remain neutral. But if you are working with brine, do appreciate that the whole solution will become alkaline because water is reduced at the cathode, but no H plus produced at the anode. Right? So the whole solution will become increasingly alkaline if you are talking about brine. Okay? Okay, can blah, blah, blah. So let's look at checkpoint number 2. Can you work on checkpoint number 2 now? Okay, so some of you got the answer already. Should be quite simple. Are you able to find the answer? Okay, so we are working with concentrated sodium chloride. So that is analogous to using brine. Okay, so this is electrolysis. Where is the cathode? Where is the anode? Where is the cathode? Where is the anode? The one that is connected to the negative polarity will be the one receiving electron, right? So this will be the cathode. Remember? So cathode means water is reduced to hydroxide. Okay? Then the one that is connected to the positive polarity will get oxidized. Okay, so this is the anode. So oxidation is chloride oxidized to chlorine because it's brine. Yeah. Okay. So being alkaline, it will turn your solution, litmus solution, blue. So RO will become blue because it's alkaline. Then chlorine gas that is produced, right? It will turn your litmus red, then bleach, right? Because chlorine has bleaching property. It bleaches your litmus. So it will turn it, not white, it actually should be colorless because it's a solution. It's a solution, right? It should be colorless, man. Unless we are talking about the filter paper soaked in litmus solution, then that area will be white lah. Okay. Oh, anyways, doesn't matter. Answer is apple. Okay. Any argument? Okay. If there's no, then let's quickly proceed to the next part. Okay. So I don't need to show you all the thinking process, right? There's a long thinking process here. Okay. Let's skip that. Let's look at the third factor, nature of electrode. Okay, so previously, what we have been working with is inert electrode. Okay, so now we are looking at electrodes that can participate in reaction. And please take note, the reactive electrode is only considered for anode reaction. Okay, right, so can you highlight this for me? I only consider the electrode participation if it's at the anode. Must be at the anode. Okay, not the cathode. Can someone tell me why? Why? Why do I only need to consider participation of electrode if it's the anode, not the cathode? Yes, metal by default can only undergo oxidation. So if you want it to participate, it can only participate in the anodic half cell. Okay, the anode. Yeah. Okay. Then for the anode, right, if you produce oxygen gas or even chlorine gas, that can cause your carbon or graphite electrode to erode as well. All right. So sometimes your graphite electrode can be eroded. So that's why we choose the more expensive platinum electrode to be used. Okay. So this one is given to you as an example. Blah, blah, blah. So do you need me to bring you through? Okay, if not, right, let's look at the next checkpoint. Aha. Okay, let's go on the next checkpoint now. Page 12. 3 minutes. Are you able to finish? Huh? First part got answer already. How come? Alamak. Yeah. Yeah, so I will end the lesson today lah. So you all do this as homework, then I'll go through the answer the coming week, next week. So Friday, right, I will go through the revision practical. Then I'll try to return all the other booklets to you. So if you did not submit your practical booklet, right, can you bring along your practical booklet in case I want to go through stuff? Okay, depends on the time. Okay, so if time allows, I will go through, but I don't know how much you remember from whatever that I left off.